In the previous video, we constructed the binomial probability histogram. Something that I would like to add to that is the following. Remember our binomial formula that we constructed? We did the example here. For instance, if in the case of 5 successes, what if, for instance, just to match it, how do we get that 23%? Just replace that number with a 10. It will give us the 23%, exactly the same number. Or if you have 7, 7 is 0.4%, and indeed it is the same number here. There's an alternative way that I kind of try to avoid showing, and it is the following. Let me just... the reason I'm kind of trying to avoid it is because it's an Excel built-in function, Excel built-in binomial formula, binom formula. And it's also very convenient, as you guys can imagine, but it kind of, here when you painfully write the formula in Excel, put it into the cell, it seems to me it's more like there's more learning experience. But in case you want to see it, here is the formula. So you can either write p binom, I think, or in the new version of Excel, I think it's directly, you just say binom. So there's two different functions, Binom.DIST and Binom.INV. So Binom.DIST is the one that will return the probability. Binom.INV is the one you give the probability and it will tell you the number of successes for that probability, for that cumulative probability. So I will use Binom.DIST, double click. Or alternatively, we could have gone directly to the formulas and then from the maths, we should be able to find the same formula. But anyhow, going back to here, so Binom.DIST, number of successes, this number, number of trials, this number, and probability of success, probability of success of an individual experiment, that number. And is it going to be cumulative or probability mass? It will be a probability mass, so I will double click this. So this should yield the same result. Well, obviously I need to turn it into a percent with one more decimal place. Yes, there you go. So for instance, if this number was a 11, it should be 37 point. Okay, let's check. And indeed it does give. So this is the one that we painfully created using this long formula. It turns out that that long formula is just this. Binom.dist. So Excel has a built-in formula for that. All right, so having said that, we will, moving forward, use the Binom.dist formula to solve problems, obviously. And here is our example. So we have two examples here. If you want to say, let me just move this down. All right. So the first example is this one. Suppose that a lot of 5,000 electrical fuses contains 5% defectives among them. So roughly 100 of these electrical fuses are defective. The rest is in good functioning shape. If a sample of 5 fuses is tested, I am assuming that the sample is a random sample. So let's just say random sample. We randomly pull a sample of size 5 and we test them. What's the probability of observing at least one defective? 1, 2, 3, or 4, or 5 defective, right? Because we have a sample of size 5. What are these probabilities? Obviously, the probability of finding one defective, pulling a defective piece is just 5%, right? Okay, so what is the desired probability? So the desired probability that the defective one, so basically you want to find the success. Remember, successful outcome was y. You want y to be what? Observing at least one defective. So I want 1 or 2 or 3 or 4 or 5 defective. So basically you want to calculate the probability that y is if y is the number of defective ones, y is greater than or equal to 1, right? Or to be more specific, let's write it like this. Y is between 1 and, so here success is the defect, right? It's kind of weird. 1 and 5. Does that make sense? So I'm trying to avoid 0, basically. If you have a sample of size 5, maybe all 5 of them are good, which is most likely the case here, right? This probability will end up I doubt it will be too big, right? So how do I find this probability? So what I do is I need to find the sum of, well, actually, let me add the sum at the very end. So this probability will be the following. At the end, it will end up being the sum of all these things. Let me just go ahead and have a placeholder here. So here it will be basically the probability. I need first the probability of y being equal to 1 defect. So you get a sample of size 5 and you have only one of them defective. Probability of calculating y equals 2. Two of them are, you take a sample of size 5 and 2 of them turns out to be defective. Sample of size 3 and 3 of them, sorry, sample of size 5 and 3 of them are defective. Probability a sample of size 5 and 4 of them, oops, come on, are defective, or the probability of all 5 of them is very, very unlikely. This thing is basically a 0, right? That's it. So actually, this formula then is wrong, right? So, oh shoot, how did I click on this? All right, I meant to say go inside. It should be a bit more than that. So it should be really, oops, 28 here. There you go. All right, so we need to find these individual probabilities. They will add up to give me the desired probability, right? So first of all, you might wonder, wait, is this even a binomial distribution? Well, it kind of seems like, right? Because we have success or failure. In the case, success is the product being defective, and failure is the product being not defective. The probability of success is 5%. The probability of failure is 95%, even though success is, we define success as being defective, right? But the only concern is that we have a sample of size 5,000. So the first sample that I pull, yes, there's a 5% chance it is defective. But now there's 4,999 electrical fuses left, and the probability that the next one that I'm pulling that it will be defective is slightly, it depends on what was the previous one. If the previous one was defective, then it will be slightly smaller. If the previous one was not defective, it will be slightly higher. But because 5,000 is such a big number, the effect will be negligible. So for that purpose, we assume that this is indeed a binomial distribution. So having established that, now I can use the BINOM.DIST formula. So number of successes is 1. The probability, the trials, we do 5 trials, and the probability of success is 5%. And it is going to be a probability mass function. That's it. Yes. Let me make sure I'm... yes, that's it. So therefore the probability... Oops, let me put everything in percentages. That will be better. Okay, there we go. And now, so the next one will be pretty much similar to that. So actually, let me just go ahead and copy the cell, Control C. And so this will be Control V, oops, except that here the number of successes will be 2 successes, which is very unlikely. 3 successes is even worse, right? Control V, 3 successes from among 5, very, very, like it's already 0. Control V, how about 4 successes? Obviously this is 0. And finally 6 successes, Control V, sorry, 5 successes, I should say. Okay, there you go. 5, 4, 3, 2, 1 success. The sum is 23% roughly, right? So let's put this one as a percent as well, and oops, and let's have a little bit more decimal place of accuracy. There you go. So it's not exactly 0. This one is 0.1% in essence. But wait a second. When you think it through, it seems like we could have done a much faster calculation if whenever we have a random sample of size 5 and the probability of observing at least 1 defective is the same thing as 1 minus probability of observing no defective at all. Does that make sense? So alternatively, let's see if this gives us the same answer. we can calculate the probability of the complement event, right? The complement probability. So the complementary event is the probability. So the number we are calculating is really 1 minus the probability that y is equal to 0, that there is no defective one. Does that make sense? So that's just 1 minus this probability is again BINOM.DIST, and number of successes is 0. A trial of size 5 experiments. The probability of success is 0.05, 0.05, and false. That's it. And press, hey, that's the same thing, right? So it was, yes, it turned out to be exactly the same. So sometimes we might be tempted to do a straightforward calculation, but the complement should also be, you should keep it in mind. How about this question? Whenever you randomly test 20 fuses, the probability of at least 4 defects, so 4 or 5 or 6 or 7, all the way up to 20, that's too much. That's why in a question like this, we definitely need complementary probability, right? So therefore, the answer to this question will be 1 minus the probability that y is less than or equal to 3, right? Does that make sense? So 4 or more defect is 1 minus 3 or less defects. So this is equal to 1 minus okay, so I'll show it in 2 different ways. BINOM.DIST, a number of successes is 3 out of a trial of 20. Sorry for that. And probability of success is, again, like we said, 0.05, and this is false. Minus, so at this, oops, I messed up. Oh, shoot. Okay, let me just go inside the cell. There we go. I just want to copy paste. I don't want to keep doing the same thing again and again. Okay, there we go. Control V. Here I want to change that 3 to a 2. There you go. And then minus Control V. Again, the 2 to a 1, the 3 to a 1, and finally minus Control V, or 0 defects, right? So that's it. Whew. So that will be the desired probability, percent, and maybe one more decimal place of it. Alternatively, we can use the following, which is pretty cool. So equal sign 1 minus, so Control V. Okay, so here we want 3 or less, right? So we can make it cumulative distribution. So we can make it a true. Do you guys see that? Instead of, so when you do false, it gives the individual probability. When you do true, it gives all the probability less than or equal to that number. So press enter and percent. Hey, that's the same answer. So this one was a significantly go inside the cell long formula versus this one is just inside. So this is the difference between individual probability distribution and cumulative probability distribution. Cumulative probability distribution calculates the probabilities of everything less than or equal to. Pretty good. When we say everything less, so basically in a sense, let me just move this down. So less than or equal to 3 includes 0, 1, 2, or 3. So whenever you do the true logical statement, then it calculates as a cumulative. All right, so hopefully this example was useful, and looking forward to see you guys in our next lecture.